Imagine you've just trained your model to correctly classify this image as a horse. But then you look at this explanation and you see something like this. The model is simply looking at a label that is hidden inside of the image. This is very untrustworthy behavior. Imagine if you use your model on an image of another object, but with the same label, or maybe also an image of the horse, but without this label. How can you expect it to perform well? At the moment, we don't have any good action to take to correct this behavior. And this is a bigger problem in explainable AI. Currently, after we train our model, we explain it to an end user, and the end user can then review the explanation and use his domain knowledge to check the explanation. And if the explanation is correct, then everything's fine. It means that the end user can validate the model's decision, and the model will appear more trustworthy. But what if the explanation is incorrect? What can we do then? Well, currently, as you've seen before, there's no action the end user can take. What we actually would want is for the end user to be able to interact with the explanation, correct it, and that we can enforce correct explanations back into the model to improve its trustworthiness and possibly also its performance. Additionally, this is also a very nice way to both incorporate data and domain knowledge into the model training. For all these reasons, I decided to implement interactive versions of several of the most popular local post-hoc explanations that effectively allow end users to improve your models, any models. Before we get to this, I will first explain you what local post-hoc explanations are. We'll see how we can enforce correct explanations in your model. And finally, we'll see if it actually all works. Now, to understand local post-hoc explanations, let's consider a neural network that classifies this image as a fish. Now I want to explain why it makes this decision. For this, we can use post-hoc explanation methods, and they would give us an explanation like this. It's a kind of heat map which is overlain on top of the original image, and it shows you the important pixels, pixel groups, that make this image a fish according to our network. As you can also see, it's actually not that meaningful. It's quite noisy, and a lot of times these explanations look like this. What we actually would like to see is something more like this, a human annotated explanation. We see that the head of our fish is very important, also the body and the fins. It's a lot more meaningful. We would actually like our network to have these explanations. But how can we enforce these explanations back into our neural network? We can do this by modifying the loss function during training. Normally, you have a prediction loss. This time, we also add an explanation loss. And these loss functions look actually quite similar, as you can see here. For prediction loss, as you may know, it tries to get the predicted label as close as possible to the correct label. Similarly, our explanation loss tries to get the model's explanation as close as possible to our correct explanation. So now we have the loss function. The next step to training your model is optimizing this loss function, which means we have to compute the gradient with respect to the model parameters, which are given by the omega. Now, for this gradient to exist, we have to make sure the gradient of our explanations with respect to the model parameters exists, which brings us to the second step of implementing this approach. We have to implement differentiable explanations. Now, this is a bit more difficult, but luckily, I did this for you, and you can use it. What you still have to do to use this approach is add an extra loss function in your model optimization setup. Now, this all makes sense in theory, but does it also work in practice? For that, to test that, I did an experiment on some subset of the ImageNet dataset, for which we have a number of human annotated explanations like this. And I first trained without explanations, that's the middle column, and then with explanations. And these are the results. We see that training with explanations slowly gets our model's explanations closer and closer to our human annotated explanations. So in the end, we simply get better explanations and a more trustworthy model. Now, as you also see at the bottom, additionally, we see that our accuracy has increased. So finally, our model is simply a better performing model. So our approach was successful. Now, what I want you to remember is that local post-hoc explanations explain the single decision of an already trained model. You can enforce correct explanations in your model by adding an extra loss function, extra loss term, and making sure your explanations are differentiable. And finally, does it work? Yes. In the experiment I showed you, and in fact, in all of the experiments I did, we saw a better trustworthiness and at the end, a better performing model. This is why I invite you to interact with your own model's explanations. I've made my code available on this GitHub. It's under IXAI, meaning Interactive Explainable Artificial Intelligence. Currently supports PyTorch and 5 of the most popular explanation methods. Now, the next time you come across a wrong explanation like this one, you should take the opportunity to correct the explanation and conveniently improve your model. Thank you.